Okay, now let's try our first example with entropy, compressing chaos. I like to give it a fancy name. So what do we have here? We have air that's compressed by a 38 kilowatt compressor. Okay, 38 kilowatts. From pressure 1 to pressure 2. Doesn't give us the pressures. Okay. The air temperature is maintained constant at 25 degrees Celsius, which that means this is isothermal. Isothermal. During this process is a result of heat transferred to the surrounding medium at 20 degrees Celsius. Determine the rate of entropy change of the air. Okay, I like this. So how are we going to go about this? Well, remember that ds is equal to q over t. Okay, that's the kind of rough one here. I should just put a little delta there. I sometimes forget it. Okay, so what I need to know is how much heat am I transferring? Best way to find that, conservation of energy. So let's write it out. First off, basic conservation of energy. En is equal to minus E out is equal to change in energy of my system. Okay. Now, some details here that help me realize a few things. First off, this part is usually connected to some sort of change in temperature for your medium, your working fluid. And it tells us that that's maintained constant. If it's constant, it's going to be equal to 0. Okay, so we know that my change in energy with time of my system is 0. So I can just say that my energy input is equal to my energy output. Now, what's going into my system? Well, work from a compressor. What's going out of my system? Heat. And so I can write that down. My work in over time is going to be equal to my heat out over time. It's going to be equal to 38 kilowatts. So this is how much power I am sending out of my system as heat over time. Okay, so we've got a lot of the stuff we need here. Now let's go ahead and calculate that change in entropy. So the change in entropy for the air is going to be equal to my heat out of the system and then the temperature at which it's being sent to, okay? And so my temperature for the air is maintained at 298 Kelvin. And the power I'm sending it out, heat I'm sending out, is 38 kilowatts. I put those two together and I find out that I have a change in entropy for the air for this process of negative 0.128 kilowatts per Kelvin. Okay, what does that mean? It means that I'm losing energy. I'm losing useful work. Anytime we have entropy generation, we're losing energy. Now, one thing you're noticing here is like, wait a second, this is a negative sign. Why is it negative? That's because the heat is going out of my system. Since the heat is leaving my system is getting less entropic. But that doesn't mean necessarily that my entropy is decreasing in the universe. That doesn't happen. Like, here's an example. Here's my box. Here is my system. Here is the surroundings. I have heat going from one place to the other, which means that this one has a positive change in entropy, and this one has a negative change in entropy. Overall, though, the amount of entropy is going to be increasing. It always does. And we can actually see that if we wanted to, because if I wanted to calculate the change in entropy for my surroundings, it would be equal to the heat output over time, and then the temperature of the surrounding air, which would be equal to 38 kilowatts over 293. Now this, I'm not going to do the math right here, but you can see is I'm dividing by a smaller number, so I would have a bigger value. So the total amount of entropy for this process, like system and the surroundings added together, is positive, like entropy was generated. That means that useful work has decreased. That is the important thing about entropy. It's telling us how much my useful work is decreasing as I do these processes. I want to minimize entropy change as much as possible. That's going to help me out make better systems. Okay, that's it for this time. Thank you for listening. I'll see you all in a bit. Bye-bye.